All right, let's move on from redox reactions to talk about concentration. We've already encountered this a little bit. Concentration is a way of discussing how much of one substance is dissolved in another substance. If you have substance A dissolved in substance B, you can talk about the concentration of substance A. You wouldn't talk about the concentration of substance B just because there's so much of B that it is basically present in infinite quantities compared to how much there is of substance A. For example, if you dissolve 5 grams of sugar in 100 milliliters of water, you have 5 grams of sugar in 100 milliliters of water. Now, if you pour 12.7 milliliters of that sugar water out on the ground, how much sugar do you have left in your glass? Well, that's 87.3% of 5 grams is 4.37 grams. Now, let's say you take another solution, 50 milliliters of another solution that was originally 100 mils with 12.5 grams of sugar in it. Well, that's 10.62 grams of sugar in 137.3 milliliters. You can double check my math on that. I did, and I'm right because I'm awesome. But it's difficult. It would be nice if there were a better way of talking about this than just trying to keep track of what mass of what stuff is present where. And that's what concentration is for. Concentration is, well, one measure. There are multiple measures of concentration, but one is molarity. And that's moles of solute divided by liters of solution. Not liters of solvent, liters of solution. Okay. So remember, the solute is the thing being dissolved. The solvent is the thing doing the dissolving. So sugar is the solute. Water is the solvent in this previous example. And the solution is both of them together. So the sugar water. Here's your water. This is the solvent. Here's your sugar being poured in. And that's your solute. And when you have them all together, that is your solution. Now, the reason we have to differentiate the solvent and the solution is because the solute will increase the volume of the solution. They dissolve, they don't disappear. So the solution is going to have a somewhat larger, not a whole lot larger, but somewhat larger volume than the solvent. So when we talk about mixing up a solution, we'll say you add, say, 0.100 moles of the table salt to get 1 liter of solution. Meaning that you have your glass, you pour your salt in first, and then, and only then, you fill to the 1 liter mark. Okay. So 1 liter of solution, not 1 liter of solvent. Remember that. That's a fairly important distinction. It does make a difference. Sometimes a big difference, sometimes a small difference. But it always makes a difference. Now, molarity is kind of like density. Okay, you have a piece of iron with a density of you have a piece of iron with a density of, it was 9.3 grams per mil. You break it apart into 3 pieces. Each one of those is going to have the same density, 9.3 grams per mil. And then the same for all 3. Concentration works the same way. If you have a 1 molar solution of something, and then you pour it out into separate glasses, each one is going to have a concentration of 1 molar. And the density should be uniform throughout, is what I'm saying. Or, once you've mixed up a particular solution, the concentration should be uniform. So that's one big advantage of concentration. Once you know the concentration, every time after that. For example, once you know the concentration of every solution you get after that. So let us look at a few examples. Let's say you throw 10 grams of sodium chloride into a 250 milliliter solution. What is the concentration? This is something you should get used to. These square brackets mean concentration of something. So, to be technically correct, this should be concentration of sodium chloride equals question mark. Well, it's going to be moles of NaCl divided by liters of solution. So we're going to need to do a couple of conversions before we can even do this math. Okay, 10.00 grams of sodium chloride times moles per gram. We need to use the molar mass of sodium chloride. It's 22.99 plus 35.45. It's 58.44 grams per mole, meaning that our moles of sodium chloride is 0.1711 moles of NaCl. We're also going to need to convert our volume from milliliters to liters. Fortunately, that's a very simple conversion. 1, 2, 3 to the left. Remember, big unit, small number, small unit, big number. Liters are bigger than milliliters, so our number should get smaller, and we have 0.2500 liters of solution. So our concentration is going to be 0.1711 moles of NaCl over 0.2500 liters of solution, which is going to get us 0.6844 molar NaCl. That is not necessarily going to mean much to you right now. We're starting to get into some of the more abstract sorts of quantities and concepts, but that is a fairly concentrated solution. 1 molar means 1 mole per liter, and a liter of water is about the size of a Gatorade bottle. And for sodium chloride, 1 mole would be 58.44 grams. That's a big heaping handful of salt. So imagine, putting a big double handful of salt into a Gatorade bottle, filling it up with water, and shaking it till it's dissolved. That's going to be a very salty bottle of water. So 1 molar is pretty darn concentrated. We often work with much less concentrated solutions. To give you another bit of perspective, 1 molar HCl has a pH of -1. So that's very, very acidic. 1 molar is pretty darn concentrated. 0.6844 molar sodium chloride isn't as concentrated. Let's see if I can give you some perspective. I know many of my students have been nurses or prospective nurses in the past. Let's do a quick conversion from a 9% sodium chloride or saline solution. A 9% saline solution is actually 0.9% by mass. So 0.9% means 0.009 grams of NaCl over 99.991 grams H2O plus 0.009 grams NaCl. And now I get to tell you that I made a slight mistake there. It's 0.9 grams per 100 mils of solution. So all of my work moving forward is going to be about 100 times too small, including the final answer I come up with. I caught my mistake. That means I'm awesome. So 99.991 grams of H2O. Let's just go ahead and assume it's at room temperature. It's nice. And normal is 99.991 milliliters of H2O. Assuming density equals 1 gram per mil. Trying to throw density calculations in there would just make this really nasty. The other thing we're going to have to do is assume NaCl has no volume. So the total volume of our solution is equal to the total volume of the water. That is definitely a cheat, but I'm going to stand by it, just because I don't want to try and find out what it might actually be. So, 0.009 grams NaCl times 1 mole for every 58.44 grams gives us 1.54 times 10 to the negative fourth moles of NaCl. And 99.991 is 0.099991 liters of water. Which means, for those of you who are curious, that the concentration of 9% saline solution is 0.00154 molar. 0.154 molar. I blame Richard. That is a fairly difficult sort of problem. You have to make a couple of simplifying assumptions before you can even start on it, but otherwise it's pretty straightforward. That you just convert from grams to moles, and then you just divide moles by concentration. Liters, damn it! No more recording marathons. And that gets you your molarity. So molarity is definitely something you're going to want to practice. And believe me, you're going to be getting plenty of practice. If you don't, you'll wish you had. As per usual, all roads lead to mole. Because molarity is the relationship between moles and volume, given any two of these three, you can find the third. They give you concentration and the number of moles. You know what volume of solution you'll need. If I give you concentration and volume, you'll know how much stuff is in it. And if I give you moles and volume, you know the concentration of that particular solution. Let's work out a quick couple of examples. If you want 5 grams of ammonia, you have a 0.100 molar solution of ammonia. What volume of ammonia solution contains 5 grams of ammonia? And first, you convert to moles. All roads lead to mole. So you divide by 17.03 grams per mole. That gets you 0.294 moles of ammonia. Now we have molarity equals moles over volume. Solve for volume. Volume equals moles over molarity. So 0.294 moles of ammonia divided by 0.100 molar ammonia This is moles per liter. The moles will cancel out, and liters will come up to the top. And that gets us 2.94 liters of ammonia. That's a lot. But then 5 grams of ammonia is a lot, and 0.1 molar is not particularly concentrated. Note that if it were 1 molar, 1 molar would mean 0.294 liters, 294 mils, a much smaller quantity of the ammonia solution. All right. We'll go ahead and call it for this lecture. When we come back in the next lecture, we'll work another example before moving on.